Hi, algebra classes. This is Mr. Ye, and I wanted to make a quick video with you about quadratic functions and specifically the main features of graphs of quadratic functions. I know we've seen quadratics and parabolas a little bit, but I wanted to really formalize a few concepts. First one that we need to discuss is what is a quadratic function? Well, simply put, it's a function where the highest degreed term, the highest term, has an x squared. Okay, so the highest degreed term, the degree is 2. And in standard form, as you see here, we say that the function f of x is equal to ax squared plus bx plus c. That means some number a, and it could be lots of different numbers as we will see, number of x squareds, and then some number of b's, and then some constant number for c. So this is called standard form of a quadratic. A couple examples might be f of x equals 5x squared minus 17x plus 4. And I apologize for my handwriting, but 5x squared minus 17x plus 4. Well, if I asked you, what does a equal in this equation? A is the number of x squareds. A is 5. What does b equal? Negative 17. That negative does go with that b value. And what does c equal? C equals 4 in this example. Let's do one more. I'll name this function g of x. Remember the function names can vary. Equals negative x squared plus 9. And you might be thinking to yourself, wait, standard form needed a number of x's as well, a bx. If I asked you what a was, many of you would probably say, how many x squareds are there? Well, there's negative 1x squareds. And what is c? C is just that constant, just the number, so c is 9. What is b? Well, how many x's do we have? We don't have any x's in this function. B is just 0. And another way you can think of it, I'll write it above, negative x squared plus 9. If we wrote in plus 0 x's, would anything change? No, because 0 times x is just 0. That won't change anything. So that's how we can see that b equals 0 on that function. Okay, now these a, b, and c values are going to be really important when we're finding some of these other features. So make sure you feel comfortable knowing a is the number of x squareds, b is the number of x's, c is just the numerical part, just the number, the constant. Now, the shape of a quadratic function is always going to be a parabola either opening up or opening down. Let me grab the highlighter. So this first function that I have graphed on the screen, y equals 2x squared plus 4x minus 3. That's kind of the red maroon one. That is this parabola right here. And I kind of missed the bottom. There we go. That is the graph, the visual representation of y equals 2x squared plus 4x minus 3. Change color really quickly. Y equals negative x squared plus 2x plus 4. That is the blue graph that I am also highlighting in a lighter blue. These are two examples of parabolas, kind of like arches or upside down arches. And these two parabolas, one of them opens up. The yellow one opens up and the blue one opens down. Now, I have a little fill in the blank on the right side of your screen, and you might already know this, but if the a value is greater than 0, and I'm going to look right here at my a value on that red highlighted in yellow parabola, the number of x squareds was 2. If the a value is greater than 0, that tells us that our parabola is going to open up. I like to think of it as a greater than 0. That means a is positive, and positive people smile a lot. So it makes a little smiley face. It opens upwards. In the second example, a, how many x squareds do we have? A was negative 1. We have negative x squareds. If a is less than 0, If A is negative, the parabola is going to open down. Negative people, they frown a lot. So we have a frowny face parabola when A is less than 0. Okay. Now, two kind of additional facts that hopefully make a lot of sense. If a parabola opens upwards, it will always have a minimum value. And let's just kind of picture this. If I have an upwards opening parabola, there is definitely a lowest point here, a minimum value. It goes up forever on both sides. So I don't think there's a maximum value, but there is a minimum value, a lowest point on that graph. And conversely, if a parabola is opening down, we definitely have a highest value, a top of that parabola. But we don't have a minimum value because it goes down forever. So if we have a parabola and let's say its A value is negative, that means we know it's opening down. And if it's opening down, if you can visualize that parabola, that means we will have a maximum value because it opens down and goes down forever. If A is positive, that means the parabola opens up. And if the parabola opens up, it will have a smallest minimum value. How low does it go? There is a lowest point on that graph. Okay, so those are some of the first basics that we want to talk about when it comes to finding features of our parabolas from our quadratic equations and quadratic functions. I'm going to put on the screen now a few other key features of parabolas. And I'm going to sort of just make a sketch on the right-hand side as we talk about all of these. The first one that I'm going to talk about is the axis of symmetry. Now, if I draw a parabola over here, and I'm not going to be very careful with it, it looks something like that. Well, the axis of symmetry, symmetrical or symmetry means the same on both sides. There is going to be a line, a straight up and down line that we can draw that will cut the parabola in two, and the left and the right are mirror images of each other. We could fold the left side over onto the right, it would line up exactly. This right here is my axis of symmetry. It's my line that cuts the parabola into two perfectly equal halves. And we can find the equation of that line. It's an up-down line, so it will be an x equals line. And we can calculate the numerical value where it is by using the formula x equals negative b over 2a. Those b and those a values, those are the same values from, I'll scroll up, from right here. A is the number of x squareds, b is the number of x's. So negative b over 2a, if we plug in those numbers, it will tell us where is that axis of symmetry. Now, we're going to see this in an example coming up soon. I also want to identify a few of these other features, though. The x and y coordinates of the vertex. Well, before we talk about those, we should probably talk about what is the vertex. On the parabola, in purple, I am drawing that vertex right now. It's a point right in the center of that parabola that is either the lowest point or the highest point, maybe if it's a downward facing parabola, but it is either the valley or the peak of our parabola. And the good news is, if you think about it, because it's in the middle of the parabola, that means it's always on our axis of symmetry. And so how do we find where it is, what the x value of that point is? It's going to be the exact same equation as the axis of symmetry, negative b over 2a, because it will always lie on that line. Now the y coordinate. I have on my notes here, just plug in the x coordinate, plug in whatever value we get for the x coordinate into our function. Just like we always plug values into our functions, whether they're quadratic or not, we plug in an x value and we simplify and we get what the y value is. That's the same thing for the vertex. And you will see that in some examples coming up. So this is the vertex. We can find the x-coordinate with negative b over 2a. We can find the y-coordinate by plugging in the x-coordinate. We also have x and y intercepts. Now, the y-intercept happens to be the c value from the equation, just the numerical part. And I'm going to mark the y-intercept just to remind you on the graph. This is my y-intercept. This y-intercept is where our graph crosses the y-axis. Wherever it hits the y-axis, that's the y-intercept. And it's really easy to find from the equation. It's just the c value. Now the x-intercepts. And we need to talk about the x-intercepts a little bit here because there are three scenarios. It's possible, and in many parabolas, I'll go dark purple, it's possible that we have two x-intercepts. We cross the x-axis twice. It's also possible, I'll draw a downward opening parabola, we only have one x-intercept, where we only hit the x-axis one time. And you might have already seen where I'm going with this. If you look at this purple parabola that I just drew, it has 0 x-intercepts. It never hits the x-axis. Now, for right now, we are going to find those x-intercepts by graphing and then figuring out where did we hit the x-axis. On this example, the one that I've been mainly working with, it looks like there are two x-intercepts. There's one here, there's one here, and I'll just label those as my x-intercepts. Okay? These are most of the features we're going to look at for our quadratic graphs. And so now we're going to get some practice finding what they are in an actual example. So our first example here, it says find the direction of opening, the max or the min, the axis of symmetry, the vertex, the y-intercept, and the x-intercepts of the parabola below, and asks us to sketch the parabola by making a table of points. So we're going to do this one together. F of x equals x squared minus 4x plus 3. Now, direction of opening, we don't have to do too much for. We have positive x squareds, positive 1 to be precise, a is 1. And if the a value is positive, I know that I'm going to be opening upwards because positive people smile. So I'm going to make a tiny little sketch here. I know it's going to look something like that. Will it have a max or a min value? Well, if you think about that sketch, I can see that it has a bottom point. It has a minimum value. I don't know what it is yet, but I'll figure out how low this graph goes and put the exact value in there soon. All right, let's do axis of symmetry. So axis of symmetry, I'm going to change colors to be blue. We know that the axis of symmetry can be found with the equation x equals negative b over 2a. And I'm just going to say x equals negative, what is my b value in this function? Looks like negative 4. I didn't circle that very well. B value is negative 4, so we get negative 4 over 2, and what was my a value? Positive 1x squareds, so a is 1. So that means that x equals negative 4 is positive 4. 2 times 1 on bottom is 2. My axis of symmetry is the line x equals 2. And I can come to my graph, and I'm going to try to align this really quickly, just a little bit, move it up so it's lined up with my graph paper background. X equals 2, I'm going to come out here to 2, and I'm going to draw in my axis of symmetry. Now, as for the vertex, this is also not too bad because I actually know that the x-coordinate of the vertex is going to be positive 2. It has to lie on that axis of symmetry. So with that in mind, How do we find the y value of the vertex? If you remember, I'd said earlier, we're just going to plug in the x coordinate into our function. So let me come up here to the top real fast and just say, what is f of 2? Let's plug that in. We're plugging 2 in every time we see an x, so that means 2 squared minus 4 times 2 plus 3. 2 squared is 4. 4 times 2 is 8 plus 3. 4 minus 8 is negative 4 plus 3. I believe that is negative 1. So when we plugged in 2 into our function, 2 from the axis of symmetry, we got negative 1. That means my vertex is going to be at 2 comma negative 1. And I'm going to put that on my graph, 2 comma negative 1. Now, the other thing, and I didn't mention this before, but now we can, I know what my minimum value is. My minimum value is going to be negative 1, because remember, if that's the vertex and this is opening up, it will look something like that. So what was the lowest that our parabola went? The lowest was negative 1. Guys, the max or the min is always going to be the y-coordinate of the vertex, because the vertex is the lowest or highest point. And so we know that the vertex, the y-coordinate was negative 1. Now we know that the minimum value is negative 1. All right, y-intercept, if you remember, is just the c value. It's going to be 3. 1, 2, 3. I can plot that because I know I hit the y-axis there. And the other nice thing is because parabolas are symmetrical, and I'm going to zoom in really quickly on the graph, they're the same on both sides. They're symmetrical. I went 2 units to the left, and my point was at a y value of 3. That means I can go 2 units to the right, and I know that there will be a point at that same y value. It's going to be symmetrical. All right, the last thing on our list to find, and it also goes along with the sketch, x-intercepts, and we need to sketch by making a table of points. Here's my recommendation. My recommendation is find 5 points. And if you notice, we already have 3 of them. I'm going to put my vertex smack dab in the middle of this table, 2, negative 1. We already found that was a point. And then it's nice because we also already found the y-intercept, which is when x is 0, because that's when we hit the y-axis. We were at 3. And by symmetry, we went 2 the other way. 4 for the x value was also at 3. So even though I say find 5 points, we've already found 3, and if we find one more, we can use some symmetry to reflect it across that axis of symmetry. 0, 2, 4. I think I'm just going to try 1. 1 seems like a nice, easy one to find. If I plug 1 into my function, we get 1 squared minus 4 times 1 plus 3. 1 squared is 1. 4 times 1 is 4, so 1 minus 4 is negative 3, plus 3. 1 comma 0 is a point on this parabola, which means we can reflect that across the axis of symmetry, 3 comma 0. Just like that, we have our 5 points. We know that our parabola will look something like that. Let me redo that second half. I kind of missed both of those points. Drawing is hard. Okay. And what are the x-intercepts? Well, from the graph, where did we hit the x-axis? It looks like when x equaled 1 or when x equaled 3. Those are, and I'm going to draw arrows, those are the spots I hit the x-axis. So this is just a quick example of how we can find all those different features on a graph. Okay, let's try another one. I'll go through the next example a little more quickly because we've done it once already. Direction of opening for f of x equals negative 3x squared minus 6x. Well, we see we have a negative a value, which I hope you remember that means we are opening down. And if I'm opening down, do I have a max or a min value? I definitely have a max value. I have a top value. I don't know what it is just yet. I'll find it. I'll find it soon. Axis of symmetry. We know that the equation is x equals negative b over 2a. Negative, what was my b value? Negative 6, it looks like. So negative 6 over 2 times a was negative 3. 6 over negative 6, negative 1. So the axis of symmetry, x equals negative 1. And I like to just kind of start my graph off with my axis of symmetry. So I'm going to draw a line, not a keyboard, draw a line right there where x equals negative 1. And that's my axis of symmetry. Let's go ahead and find our vertex. I already know the x-coordinate because it's on the axis of symmetry. And now I just need to figure out what is my y-coordinate. And I'm going to do that by plugging it into the function. Now, I know that negatives can be a little tricky, so we just got to be careful. What is f of negative 1? That means we have negative 3 times negative 1 squared minus 6 times negative 1. Order of operations, I'll do that squared first. So negative 3 times 1 plus 6, because negative 6 times negative 1. So negative 3 plus 6, which equals 3. My vertex is going to be at negative 1, comma 3. 1, 2, 3. I already know it opens down. I'm starting to get a visual of this. I know my maximum value now because if it opens down, 3 was the highest that I went. Y-intercept, what is the C value on this? It's a little hidden because it doesn't appear, but remember, we can always put a plus 0 on the end without changing an equation. If C is 0, the y-intercept is at 0. And because of symmetry, I know there's a point right here too. I also actually kind of know the x-intercepts then, as it turns out on this problem. Because where do we hit the x-axis? It looks like at negative 2 and at 0. So I'll go ahead and write out the full x equals negative 2. Or at 0, that's when I hit the x-axis. And as I said, I'm a big fan of always having 5 points. I'm going to move my table up here because I know it won't interfere with my graph because my graph is going down. The vertex was negative 1, 3. Then we had negative 2, 0, and 0, 0, those 2 points on the graph. I'll plug in 1 and see what I get. I'm going to do the scratch work down below because I have a little more room. What is f of 1? That would be negative 3 times 1 squared minus 6 times 1. Negative 3 times 1, because 1 squared is 1, minus 6. Negative 3 minus 6, and that's going to equal negative 9. So when x equals 1, I need to go all the way down to negative 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And because of symmetry, I can go 2 to the left and find that I'm also at negative 9. And here is my sketch. Here's that sketch. I kind of missed the second green point, so I'll redo that. If you can't tell, drawing is not my forte, but that's all right. Again, finding all those same features on our graph. Okay? One more example like this, and feel free to pause this video and try this on your own. See if you get the same thing I do. I'm going to add the 9 in my table real quick. Last one. Feel free to pause it, try this, finding all those features and sketching the graph, and then unpause it when it's time to go. All right, I'm going to assume you've tried this one. Direction of opening, A is negative. That means we are opening down. It's going to be a little frowny face, a little negative frowny face. And that means I have a maximum value. Don't know what it is yet, but we will find it soon. Axis of symmetry, x equals negative b over 2a. That means negative 6 over 2 times negative 1, 6 over negative 2, negative 3. X equals negative 3. And I know I'm going through this one really quickly. Since you had time to work on it while the video was paused, I will not rush it, but go through it at a pretty good pace. So x equals negative 3. There we are, axis of symmetry. That also tells me that negative 3 is the x-coordinate of my vertex. I just need to find the y by plugging in that x value. So f of negative 3 is negative 3 squared minus 6 times negative 3 minus 9. Be careful with your signs and your order of operations. Negative 9 plus 18 minus 9. Negative 9 plus 18 minus 9. Looks like that's going to be 0. So negative 3 comma 0. And that means my max value is, how high did that go? I mean, if that's the vertex and I'm opening down, my max value is 0, which is weird because max value doesn't seem like it should be 0, but let's see what happens. Y-intercept looks like negative 9. It's just that C value. So 1, 2, 3, 4, 5, 6, 7, 8, negative 9, 3 to the right of the axis of symmetry. That means I can go 3 to the left and also get negative 9. And then we need to sketch, we need to get our x-intercepts. So x, y. I know that my vertex is at negative 3 comma 0. I know that I have, go green, 0 comma negative 9 and negative 6 negative 9 it looks like on my graph. And I'll just try plugging in one other kind of easy-ish value. I'm going to try negative 1, which is 2 away to the right. Negative 5 will be 2 away to the left. If I plug in negative 1, f of negative 1 equals negative 1 squared minus 6 times negative 1 minus 9. Negative 1 plus 6 minus 9. Negative 1 plus 6 is 5 minus 9. Sounds like negative 4 for these two symmetrical values. So negative 5, negative 4, negative 1, negative 4. What are my x-intercepts? Well, in this case, we only have one x-intercept. This is a case where the vertex is on the x-intercept. We go up to it, and then we go down away from it. So x equals negative 3. Looks like the only x-intercept. All right, lots of features of graphs. There's one more thing I want to cover, and that is the domain and range of quadratic functions. So domain, if you've forgotten, domain describes which x values exist for this function. Which x values is this function defined at? And if you look at this parabola here, the x-axis is left, right. I'm going to add arrows to remind us we go forever left, forever right. The domain is all real numbers. And every x value is in the domain of this function. One kind of shorthand way to write that is a double-stemmed R, kind of a fancy R, saying all real numbers. Now, the range describes which y values appear with this graph. And if we look at this graph, the minimum looks like negative 1. That's as low as we go, but we go up forever. So I'm going to say that y is greater than or equal to negative 1. That's my range. That's saying on this graph, I will hit everything negative 1 and above because the lowest point we go is -1, and we go up forever, the range is y is greater than or equal to -1. Let's look at another example. Domain here, well, we go left and right forever with no breaks. I think it's going to be all real numbers. The range, it looks like our maximum was 3. That means what y values do we hit? We hit everything 3 and below. Y is less than or equal to 3 because we hit 3, we hit 2, we hit 1, we hit 0, we hit -1. All of those are hit by our graph. All those y values appear in our graph. And then lastly, what is the domain of this function? It goes forever left, it goes forever right. If you were thinking all real numbers, you were correct. And fun fact, the domain of every quadratic function is all real numbers because they're all parabolas that go left and right forever. So that's kind of a neat, nice little shortcut. The range, the maximum here, the maximum y value we hit is 0, and we go down forever. Y is less than or equal to 0. So we've covered a lot in this video, a lot of different features of quadratic functions. We started just by talking about A, B, and C, what they were. We talked about the direction of opening, and if it opens up, how it has a minimum value. If the parabola opens down, it has a maximum value. We looked at axis of symmetry, the vertex, the y-intercept, the x-intercepts, and we practiced graphing. 3 examples, finding each of those features. Axis of symmetry, direction of opening, max or min, vertex, y-intercept, x-intercepts. We sketched the graph through a little table, just plugging in points. We did that a few times. And we ended here with domain and range. Domain and range of quadratic functions. Domain is which x values get hit on our graph. And for parabolas, I said that's all of them, which is kind of nice. The range is not going to be all real numbers. It's which y values get hit on our graph. Well, on this first one, anything -1 or above, so y is greater than or equal to -1. On the second one, anything 3 or below, so y is less than or equal to 3. And the range on the third parabola, anything 0 or below, because 0 is the highest y value we hit, y is less than or equal to 0. So everyone, I hope that this video going over the features of quadratics was helpful. I know you've got some practice and you've probably been working on it during this video. If you have questions, please feel free to ask. Otherwise, best of luck with these quadratic functions. And always feel free to come find me if you have any questions. Have a good one.